Hey, I'm Amy Wang, and this is my presentation on Lab 3, the black hole orbit. The objective of this lab is to observe the motion of a star from the position given by a CSV file and use that information to find the mass of the black hole the star is orbiting. The result I received from computing the lab using Newton's gravitational force principle and the connections between F-net components and the change in momentum components was that the mass of the black hole equaled 4.78 times 10 to the 31st kilograms. Now let's talk about the models I used to compute this lab. There are two main ones, with the first being the momentum principle. The momentum principle in its derivative form is delta P over delta T equals F net. So the change in momentum is equal to the net force acting on an object times the duration of the interaction. This is true for a small delta T. The next model used is Newton's gravitational force principle. Newton's gravitational force principle states that there is a force of attraction between all masses in the universe. The equation is basically describing the fact that the specific force of attraction is proportional to the product of the two masses and inversely proportional to the square root of the distance between them. The constant g in the equation is equal to 6.7 times 10 to the negative 11. To find the mass of the black hole, we have to use this equation here. This equation can be transformed into this line of code, which is added to my module. To run the code successfully, I had to first put in all of my initial conditions. In the first three lines here, we have the star's mass, the black hole's position, and the time elapsed, which were all given. Here's where we include the CSV data with the star's position as time elapsed. The first while loop here is used to compute the velocity of the star during its orbit around the black hole. In the second while loop here is where we input all of the previous physics models. Let's look at it in detail. We first define V final and V initial here. From this, we can find the initial and final momentums by multiplying the star's mass by its corresponding velocity. And now I am able to find change in velocity and change in momentum. dp dt equals change in momentum over change in time, which from the momentum's principle we know to equal F net. Then I find the direction of the momentum by dividing the initial momentum by the magnitude of it. I then find the magnitude of the parallel component by dividing the change in magnitude of the momentum by delta t, which I multiply by p hat to find the parallel component of dp dt, which I know to be the same as F net parallel. Because I know that the parallel and perpendicular components of dp dt add to equal it, I can find the perpendicular component of dp dt by subtracting the parallel component from it. And I know that I can set this equal to F net perpendicular because of the momentum principle. Now let's run the code. We can see the star orbiting the black hole. The arrows represent the various components. The blue is the F-net perpendicular. The black is the F-net parallel, and the yellow is the total net force. The perpendicular component is larger than parallel because that is the direction of motion. We also need to remember that the only force being acknowledged is the gravitational force, which has a strength inversely proportional to the distance it acts on. Let's look back on the code. Here we added the line of code derived earlier from the universal gravitational law to find the mass of the black hole. All the values are known, so when the code is run, the mass is printed. In conclusion, I found the mass to be 4.7 times 10 to the 31st kilograms. Let's answer the first question of what does it mean. The momentum principle states that F net equals dp dt, and that the parallel and perpendicular components of F net and dp dt also equal each other. However, they are different in the ways that they are calculated. To find F net in this case, we just need to look at the universal gravitational law to find the gravitational force. To find dPdt is more tedious because you also have to find the velocity and use the principle P equals mv to figure out the answer, just as we did in our code. The net force can be found by just adding up all the forces acting on the object, whereas dPdt is found by just observing the momentum of the object itself. Also, dPdt doesn't affect the star's motion while Fnet does. So even though they are equal by the momentum principle, they are found in different ways, making them different. Now let's move on to the second question of what if. The answer is no, because if the star position data points and the motion of the star remain the same, there is no other way to calculate the mass because there is no alternative gravitational force to give a different answer. If we were given different points, we could calculate a new mass and see a difference, but in this case, the answer is no. Thanks for watching my Lab 3 presentation on the black hole orbit.